Alright, so in this video we're going to be talking about the DBSCAN algorithm. So DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. So you can see I'm going to be going through the notes here with you, and that's because I really want to refer to the figures in those notes. Okay, so I'll kind of jump back and forth between the notes and like the little whiteboard over here on the side. All right, so the idea behind DBSCAN is we're going to try to extract clusters from the data, but we're not going to necessarily have cluster centers. We're just going to be able to identify which points belong to which clusters. Okay, and we'll also, the nice thing about DBSCAN is we'll also be able to classify some data points as noise, which the other algorithms will not do. Okay, so that's really the big feature of DBSCAN, is you'll be able to kind of cluster, you'll be able to find clusters and then be able to perhaps extract noise. You do have to be careful when you're defining your noise. Okay, so the way this is going to work is DBSCAN is going to separate the data into three sets: core points, border points, and noise. Okay, so what is a core point? A core point is a point P where if you draw an epsilon neighborhood, where epsilon is a parameter for the algorithm, fixed parameter for the algorithm, then we must have at least min points within that epsilon neighborhood, and that includes the point itself. Okay. By the way, that also includes the border point. Good. So again, point P is a core point if, when you draw an epsilon neighborhood about P, you have at least min points in the epsilon neighborhood. Good. Now a border point is a point where if you draw an epsilon neighborhood about it itself, so this is my point Q, and I've got epsilon here, it's not going to have min points here. There's not enough points within the epsilon neighborhood. However, it's a border point if it's within epsilon of a core point P. Okay, so if it's in, so I guess I should write that down. So a point is a border point if it has less than min points in its epsilon neighborhood, but, or I should say and is within epsilon of a core point. Okay. And finally, we have noise. A point is noise. So P is noise here if it has less than minimum number of points and it's not a border point. So it's not within epsilon of any other core point. Okay. And so these are the two parameters for this algorithm. The two parameters are epsilon and min points. Okay, so you have to set those in advance, and so those are the arguments that you'll see being passed into this algorithm. Good. All right. Now there's some ideas here that we need to talk about, and it's kind of based on how this algorithm is going to work. What we're going to be doing is we're going to select a point at random, and then we're going to check to see if it's a core point. And if it is a core point, we're going to start looking at each of the points within the epsilon neighborhood and check to see if those are core points. And then we're going to check those points to see if those points are within if those points are also core points. And so the way this is going to work is we're just going to be expanding this cluster out, okay, using this idea of a core point. And so in order to do that, there's a couple of ideas that are really important. And those ideas are, if I can get the page to flip, where is it? Density reachable points. Good. So let me expand this out to fill the window here. So a point is directly density reachable from a point P if point P is core, that's important, and Q is in the neighborhood of P. Okay, so in this figure I wanted to emphasize, right? So in this case, min points is equal to 4 here. Sorry about that. Min points equals 4, and whatever epsilon is, right? And so, yeah, this is the epsilon neighborhood around P. And how many points are there there? There are. I better not use white. There's 1, 2, 3, 4, 5. Good. So therefore, of course, P is a core point. Good. Now point Q has how many points within its epsilon neighborhood? 1, 2, 3. Okay, therefore Q is not a core point, so Q is a border point, right? Now, we would say that point Q is directly reachable from P. Point Q is reachable from P. Gosh, I don't have a color black, I don't think. Gray, I guess. P is directly reachable from Q is directly reachable from P, but is Q directly reachable from P? Is P directly reachable from Q? Did I say that right? Well, in order to be directly reachable like that, the point that you're coming from has to be the core point. And so in this case, Q is not core. Therefore, P is not directly reachable from Q. Does that make sense? Let me start over again. Just to repeat this. So a point P, or a point Q is directly density reachable from Q. I'm thinking one thing and saying another. A point Q is directly reachable from P if P is a core point and Q is in the epsilon neighborhood of P. So here we go. There's a couple things you got to check, right? So is Q directly reachable from P? Is P a core point? Yes. Is Q in the neighborhood? Yes. So therefore, Q is reachable from P. Q reachable from P. Now let's reverse that. Is P directly reachable from Q? Is Q a core point? No, stop. Therefore, Q or P is not reachable from Q. So P is not reachable, directly density reachable. I'm abbreviating that. That may be DDR, directly density reachable. This is an engineering style thing here from Q. Good. All right, so that means that directly density reachable is not symmetric. Not symmetric. Good. Okay, this is why I wanted to use the PDF file here for these notes or for these pictures. So we're going to drop the directly and just say, is it density reachable? So density reachable means that you can find a chain of core points to get from one point to another. Okay, so a point P is density reachable from Q with respect to epsilon and minimum points if there's a chain of points where P1 is starting from Q, right? And Pn ends at P, such that Pi plus 1 is directly density reachable from Pi. Okay, so this is trying to get P from Q, right? A point P from Q, P from Q. So here's P from Q, and so P from Q is reachable through R, right? Because um, P is directly reachable to R, and R is directly reachable to Q, from Q. Um, but yeah, Q is not directly reachable from P, right? And so we had to go through this intermediary is the idea there. Okay, so that's density reachable. Again, density reachable, you can use a chain of points to kind of tie one point to another. Very good. And so the last thing I want to talk about in this video is density connected. So a point P is density connected to point Q. By the way, density connected is probably the most intuitive thing here. If there is a point O such that both P and Q are density reachable from O with respect to epsilon and min points. Okay, so that means that we could say that P and Q are tied together, density connected through this O here, right? And so what's nice about this is that if P and Q are density connected, then Q and P are density connected as well. So there's a symmetry here, right? And so that's why this is kind of a nice, this is a nice idea. Okay, so by the way, I should say there was something funky going on here that I can't remember. I wanted to, was it this picture or the other picture? Well, I think it was this picture. So one question we might ask is P core point? I think you can see with minimum number of points is 6, it's not a core point, right? Same thing with Q. Q is not a core point. But they are both reachable from O, and so that's why they are density connected. All right, so I'm going to stop here. We're going to talk about the algorithm next. The algorithm actually goes pretty fast because what we're really doing is just finding all points that are density connected to a core point, and that is the algorithm. Okay, see you in the next video.